Okay, good morning, everyone. I'm Huihuo Zheng. I'm also in the same group, AI and ML group in the ALCF, and I work a lot on the data management, data loading, I/O. I don't know if any of you kind of encounter any I/O issue or data loading issue. This is the right talk that you should focus on. If you are particularly dealing with a huge volume of data, like 3D volumes or image data, then you want to kind of focus on the techniques that how to optimize this I/O performance. And so this, I will go through the slides for about like 20 to 30 minutes. And then I do have some hands-on example and for you to try out. So first, so basically the goal of this, after this 1 hour, I hope that all of you understand data pipelines and then also know some available packages that you can use for doing this data loading in your AI training. And then also know how to optimize, what are the potential kind of bottleneck and some optimal setup on our system that you should use in order to efficiently load the data. And because we have like expensive GPU, and we hope that majority of the time is happening on GPU, right? Not waiting data. Otherwise, we'll waste the GPU cycle. And then the hands-on example just is very simple. Probably if for those of you already doing AI training, then you're probably already quite familiar with this hands-on example. And so let's define what is the data pipeline. If you Google this term data pipeline, and you'll find out that different articles say different things, but overall, it's essentially prepare the data for the AI training, right? But of course, if you consider the whole thing, whole process, it actually involves a lot of things that you maybe generate data from your experiments, but that data cannot be used right away to train your model, right? So you have to do data cleaning. And if you do AI training, you download a lot of corpus from the website. And you also have to do deduplications, and then store the data in the right format, and then develop the library to load the data, pre-process the data before you can send to GPU to do the training, right? So in generally, the term data pipelining include the entire process of preparing the data, downloading the data, transferring the data, and then loading the data, training the model, right? Even include like you load the data to the host and then transfer it to GPU. So that is the whole kind of data pipelining. But of course, today, what we'll be focusing on is a kind of a narrow scope. We assume that you already have the data stored somewhere. This is kind of you finish the data deduplications, cleaning, etc. Now all the data is sitting on the storage space, and then we want to load that data, process the data, transform the data, and then eventually transfer to GPU for the training, right? So, and a lot of this process of loading the data, pre-processing the data are happening on the host. And then after that, you make the data ready to the GPU. So GPU will do the computation, right? So what I mean in this talk is all the box belong to CPU, okay? And now, if you look at the software stack, basically on the, you may want to kind of switch the order, but basically the lowest level is the storage. Everything starts with the storage. now you have the I/O library because your data may be image data, then you want to use the image data loading library, or it's a NumPy array or HTML5 file, whatever have been generated from your experiments or from your simulations, then we use the I/O library to load the data, right? After that, we send it to a bunch of framework data loading library. For example, TensorFlow, we have the TF data. Later on, I will go through some example in the later slides. And PyTorch also have the Torch dataset and Torch data loader to load that data. And then other frameworks like Hugging Face, web dataset, etc. And eventually, after all of this, you have like the dataset batch by batch be fed into the AI model, right? So this is the whole kind of process from the software stack perspective. And then when we talk about pipelining, is essentially you have the loading, the I/O aspect, and then do a bunch of transformation. And this transformation include, for example, if you are dealing with the image data set, you may want to crop the image or rotate the image, resize the image. All of those are included in the transformation, right? And also shuffle the image. And then typically we do the training batch by batch, right? The batching and pre-processing, everything is included in the transformation or the pipelining, right? And so now just a few examples. Some of you may probably already familiar with this, is that this is a kind of a code snip from the TensorFlow using the TF data, right? So the file, all the files here are stored in the TF record format. The TF record was invented because initially, if you train ImageNet models like ResNet 50, the data set initially was a bunch of PNG files or JPG files, very small and huge amount of files. And that created a lot of I/O problems. Like, for example, on raster, that places a lot of burden on the metadata access. And so TF record format was created in a way that you can kind of put a bunch of photo and image together into a single TF record file, and then streaming those data in. And then so you have like reading those data from the I/O buffer, and then pass, you can see the map function here is doing the operation. So the pass function basically decode those I/O buffer data into image data. And then you can do number of multiple parallel codes. I will mention a little bit more later, but basically you can use multiple threads to load the data concurrently to improve the performance. Then we shuffle all the samples, right? In machine learning training and deep learning training, the shuffling is important in the stochastic gradient descent algorithm when you want to train the AI model. And then you batch it. So this will be 128 images per batch, right? So this is the batch size. And you also have the prefetch. Prefetch means that before you actually start the training, this data loader will help to prefetch a bunch of batches to the memory to be ready before the training. And then the TF data auto-tune is automatically determine the optimal number of batches to be prefetched. So you can see it's kind of the pipelining feature is here, right? You do mapping, after that you do shuffle, after that you do batch, and then prefetching. All right, so this is what we mean the pipelining. And of course, right now, probably a lot of the scientific AI core are not dealing with this TensorFlow that much. But when it first came out, this was pretty useful. And the same thing can also be used on the PyTorch. So in PyTorch, we're using this PyTorch data loader, and you can define the PyTorch dataset. Basically, you just the dataset, you just need to define how you are going to load each sample. So there is a function called get item, and say that if you are loading a NumPy array, then under this the get item, you will be using np.load, right? Loading the dataset. If you are your data is stored in HTML5 file, then you will use h5py to read that data in, right? So this function, just you can customly define that how you're going to load that one particular sample. And then this is the total number of samples you have in that overall data set. And once you define this data set, then you load it in and put into the data loader. And this data loader will kind of load the data from the data set object. And then in the data loader, you define the batch size, like how many image you want to put into that batch. And then also similar to the TensorFlow, you can define how many data loader workers or loading IO threads that you want to use to load the data. And later on, after you see kind of the profiling data from the data loader, you will be able to see, understand this better in more intuitive way. And we also have the prefetching and then pin memory is to pin the data into the GPU memory. So besides this PyTorch, Hugging Face right now particularly become popular because of the large language model training. And so they also have like similar library that you can use called dataset package. So you can install that pip install dataset. And then in this dataset, you can load the dataset by using this load dataset. And they're already kind of publicly available dataset. This C4 is a copper for the large language model training, a bunch of web, text data from the website. So if you can load this C4 dataset, and then again, just similar to the TensorFlow, you can do shuffle, and then you can do the map. Map is the what kind of operation you want to do after you load that text data, right? Here it was this was being prepared for training large language model. So if you know a little bit about large language model, after you load the like raw text, we have to tokenize it. And that tokenization is transforming the raw text into a bunch of tokens. And tokens are the integer numbers. And so this tokenization is a function that you defined. And so this map will call this a tokenization function. And eventually, the output of the entire thing will be stored in a Torch tensor format, right? And so this Hugging Face work both with PyTorch and also TensorFlow and other framework as well. And so it's very useful. And so in this particular example, we use this data set, but then wrap it with the data loader, PyTorch data loader, right? We define these batch sizes 128, and then number of worker equal to 4. And same thing with this. This is another quite useful data set when you have huge amount of data set, and then what you can do is to compress it, and then you have multiple compressed packages, the tuple, and then you load that. I personally haven't used it, but it kind of looks very, very useful. Similar to the kind of TF record that you can put a bunch of small files into tuple, and then multiple tuple, and this can load that the data from the tuple. This also work with the cloud, S3 cloud. So if you have the data stored in S3, this web data set kind of data loading library work with that very well. So this is the kind of the example. Actually, the data is stored on cloud. It also work on if you store the data set on our parallel file system, and these are examples you can use. And if you are training the large language model, we have developed a called blank copper data loading. And this actually is a bunch of very useful Python script in this package. This includes if you have the, you want to download the data from Hugging Face and then tokenize it. And after you have multiple kind of corpus, you want to mix them in and with different kind of mixing percentage, and then feed that to kind of framework like Maxtron DSP framework, or many people are using like Torch Titan. We just add this, integrate this blank copper to Torch Titan. So you can talk to me afterward if you are kind of training this large language model and would like to use. And we have a bunch of very useful script built throughout the years. So these are kind of the data pipelining. Of course, my kind of, the main thing that I want to talk about is performance, right? We want to make sure that you can load all the data efficiently. And this machine learning or AI have kind of distinct I/O pattern to the traditional HPC workloads. And traditionally, if you do molecular dynamic simulations or climate modeling, typically you generate the data and then you write it out. Those data are large kind of bulk data, like multi-dimensional array. And so the I/O mostly just write, regularly writing the checkpoint data. And then in terms of, the data type, as I mentioned, is multi-dimensional, either stored with binary HDF5 or NetCDF. And then it's typically single thread. Your main MPI task just loading the I/O, loading the data, and then doing the simulation, right? And then write the data. So you have a distinct phase of compute, I/O, compute, I/O, right? They are not overlap with each other. Whereas in the AI workloads, it's much more complex. And it's not just write. Also, during the training, a lot of intensive read, right? You keep reading the data. And then also the amount of data on the amount of data for your training typically is large than the aggregate space of your host, right? So your host cannot hold all the data. That's why we need those previous mentioned all the data loading library to stream the data from the storage to the host and then to the GPU, right? And then in terms of the I/O, is typically very small sample reading. Like right now, if you train like large language model, the sample size is basically the sequence length, and those are pretty small, like 8K, 4K or 8K tokens, and so that one sample is very small size, and then the data format is very kind of complex, like JSON file, raw CSV file, right, or text file. And another important thing is also multi-threaded. You use multiple workers to load the data versus in a traditional HPC workload, you just have one thread from each MPI task loading the data, right? And there are optimization that we need to consider because of that. Another thing is that now people start to really pay attention on the storage hierarchy. Like typically you have parallel file system that on Polaris we have Eagle file system, and then you load the data from Eagle, right? But we also on Polaris have the non-local NVMe drive, and which is close to the compute. It's actually on the compute node. So we can preload all the data to the non-local storage, and that will actually improve the I/O performance. I have some example shown in the later on slides. And then, so we mentioned about the data loading, like you have multiple thread loading. And this is the from one of the profiler that we developed, and for particular workload called 3DUNet. And it's loading the data with 4 I/O threads. And you can get a kind of intuitive understanding how all those threads kind of work together to load the data, right? So on the top row is the GPU kind of kernels. So this horizontal is a time. So your time evolve. And basically the GPU just continually doing compute. And then the I/O, those 4 threads here are from the CPU. So the CPU just loading the data and prepare the data for GPU, right? And then so here, because of the loading the data is fast, there's not too much kind of GPU idle time here. And then you can, the way to control how many threads are doing the data loading is from the data loader. Data loader, there's a number of worker equal to 8. Then there will be 8 threads doing here. But the data shown here are kind of 4 threads doing the data loading. And this actually is a very important optimization. Many people don't know that actually simply by increasing the number of workers immediately improve performance. Because by default, many times the number of workers is set to be 0. 0 means that we are using the main thread to load the data and then do the training. So it becomes like I/O and then compute, I/O, compute, not overlap with each other at all. Whereas if you set the number of workers, even just 1, then the CPU, then there will be multiple threads. So the I/O can be done concurrently while you are doing compute, right? So this is an immediate improvement. And so the first thing to try is always to increase the number of workers to see whether you speed up the data loading process. And if I kind of overall schematically show the whole process, is that T0 is the main thread. On the GPU, you're doing the training. And then other threads are doing the data loading. If the data loading is not fast enough, then still there will be some kind of idle time. GPU is waiting for the data to be ready. But if the data loading is very fast, then basically you can continually do the training batch by batch, right? That's one block is one training step. And in order to really understand all the low-level detail, we developed that profiling tool. And the plot that I showed is coming from the profiler that we developed. And this is called dftracer. And there are a bunch of things which I won't go into too much detail why we developed this I/O profiler, because there are already some kind of I/O profiler available, like Darshan, Recorder, and then even many kind of I/O probe provided by the Linux operation system. And we developed this dftracer. Primarily, this is for the Python workload, and it's very easy to use. And if you basically, this is the example how to modify the data loader code so that it will generate that profiler tracing data, right? So on the left, top on the left, you basically just load the import modular, and everything is can be done by Python decorator. So you just decorate the function, the pre-processing function, reading the data function, get item, right? And then it will generate this tracing result here. So this particular example, it will have the lowest I/O code, the POSIX read, and then you have the read data, which is decorated here, and get item, right? Get item. And then also pre-processing. In this particular example, the pre-processing is pretty fast, so you cannot see too much here. But basically, when we decorate this data, decorate those functions, all those function code will be seen here, right? So this is a map, the framework function to the POSIX read, lowest POSIX read. And so we can kind of understand whether this IO is fast or not, meeting the need or not, right? And so just a kind of some simple example. This is again the UNet3D model I was running on a single GPU with the NVMe drive. The data is located in an NVMe drive, and so you can see this. The first case, I just set number of worker equal to 1. Only one IO thread to load the data. I always start with this because with this I know that how much IO, the IO and compute ratio, right? So by looking at the trace, I immediately see there are some kind of idle time here. This is our idle time. GPU is waiting for the data, and so basically IO, one batch of data loading is more expensive than one batch of training, and the ratio is roughly 1.3, right? So then I kind of know how many data loader that worker thread that I need, right? If it is 1.3, if I increase the IO thread to be 2, number of worker to be 2, then I immediately can speed up the IO, reduce the IO, right? And then so make the IO faster by two times, right? So that's exactly what happened in the second case. So number of work equal to 2. Now I have 2 threads loading the data, right? So IO is no longer a problem. We can see the compute is now happen kind of sequentially next to each other. There's no idle time, right? So in your case, you can also kind of start in a similar way, and then see first how many threads you will need to use, because we don't want to kind of create kind of a large number like number of worker like 16 etc. Right? It's not needed here. The fewer threads that you can use, the better, because too many threads will create another kind of side effect also. And another example is that with this profiling data, it can also show us a lower level detail. So here, I found out that actually the sample was initially stored with the NumPy array, and then those are kind of image data. When I read that single NumPy array data, I found out by using this profiling data, those single array is not loaded as one chunk of the data. It's actually small block. If I remember correctly, yes, it was a 256 KB, like chunk buffer size. And so basically that create problem, right? That immediately lower the performance. What I want is that they can load it all by one time, right? So I figure if I change to HDF5 format rather than an NumPy array, I immediately improve the performance, because in HDF5 format, when I use H5Py, it was loading that entire file, which is about like 100 megabyte of size, like one chunk, versus with NumPy array, you will load 256 kilobyte, like small chunk of data, and that create a lot of overhead. And so you can see before I was using NumPy array, if I just using number of worker equal to 1, I wasn't able to overlap the height or the IO overhead. But if I use HDF5 format, now immediately my IO improved, right? So I even don't need to increase that number of worker to 2. 1 is enough. And the other thing I want to mention, this is the kind of many people forgot, is it's important to define the CPU binding explicitly. So if you don't set the CPU binding, then by default, if you have multiple worker, all the worker will be put on a single core. Versus actually we want to spread into multiple core, right? So you want to do the CPU bind, and then I think the command probably need to be updated, but check our documentation to kind of define the depth and CPU binding. So basically have to spread into multiple core. And so you can see here, if I don't do any kind of binding, it's like this. So the IO time is 30 seconds versus if I spread into multiple thread, I'm a multiple core, immediately improve 5 times, right? And so this is crucial. Later on I'll update the slide with the correct command on Polaris to do the CPU binding. Another thing is the non-local storage is sometimes useful. In this particular case, I was training UNet 3D doing distributed training at large scale. At first, I was putting the data on the raster, and then you find out that if I increase the number of nodes, the raster is not kind of enough to fit the data, right? Because the peak performance from the raster file system is about 650 gigabytes per second for the data loading. So when I increase a large number of nodes, and it kind of hitting to the peak, right? But if I preload all the data to the non-local storage, because the more node I get, the more non-local storage I get, right? So it increases linearly. So this you can consider to use in your application if you really need heavy I/O in this case. So just a summary, summarize all the kind of like important lessons that we learned. First, organize the data in a kind of good way, right? This includes that you want to avoid large number of small files. You want to do kind of TF record or kind of HTML5 file, allow you to put multiple small sample into a single file, right? And then you might also want to choose like different format. If your data is raw data like a text file, you want to convert it into binary. That will immediately reduce the data volume, right? And then also try HTML5 file. I found out that it's pretty kind of useful compared to other format like NumPy array or other machine learning format. And then use multiple threading, right? Tune the number of worker, set the CPU binding, and then cache data to NVMe if you find out the data is actually very heavy. Okay, so I think have some hands-on example. Let me check the time. Perfect. Hands-on example in the GitHub repo, and it's pretty simple for you to try. And I will just go through that quickly, and then you can try later on your own time. Any questions so far for the first part?
Pio, I have one question. So your TF trace example, right? With one worker, two workers, when you use one worker, 30% of time is overhead of I/O, right? And then when you use two worker, you can hide any latency
Yes.
for the I/O, right? So I'm just curious, have you measured how much PCI bandwidth you're using for the data transfer?
PCI? I didn't measure.
You didn't measure?
But what you mean is a very important thing also. That is another important thing to consider. Actually, when I tried that on Aurora, because the GPU is fast, and then I was doing like 12 GPU, but no, I mean 12 tile, right? And that did a lot of data. And then I found out the network become a bottleneck, not able to really load that amount of data to feed the need of the GPU, right? So the PCIe bandwidth it's sometimes can be a bottleneck.
So the case you use is on Polaris?
But sorry,
The case you showed in the is on in the Polaris. So as you mentioned, if GPU is faster, PCIe bandwidth can be the bottleneck, right? And then even with more workers, you cannot hide the latency anymore, right?
that's right.
Okay.
Like in that case, the data, I mean, it will be bottlenecked by the NICs, right? How many NICs per node.
But in that case, data is sitting on the DRAM on the host, right? So you're just showing.
If you know the data, it will be loaded from the storage, right?
Yeah.
And then get injected. It need to pass through the NICs.
Okay.
The NICs, and that sometimes the NICs can be a bottleneck.
So in that case, NICs can be slower than PCIe, so yeah, that can be the bottleneck.
Yes.
So DF Tracer has any API to read some hardware counter data, or leak data, or something like that?
Sorry, can you repeat the question again?
So to measure the PCIe bandwidth or leak bandwidth, DF Tracer is able to getting any hardware counter data? I'm just curious.
So far we haven't included that hardware counter. Mostly just the I/O part. We have the providing data. The network part we're still in the development process. Yeah. So basically we have if I go back to the plot. Okay, so we have maybe this one is easier to see, right? We have the lower level data from the POSIX code. This read is a POSIX code, right? And then we have the tracing of the application function code here, right? So the lower level data right now only the POSIX-IO. But we are in the process of including other information like MPI echo, etc. And another thing is that this is because of the data is with the easy to integrate that with other tracing tool. So for example, Torch Profiler have the MPI information, right? The NICO code, 1CCL code, and then we can merge this profiling data to that the data from other profiling tools to get a kind of overall view. Mm-hmm. Any other question? All right, I will quickly kind of go through what we have on the hands-on example. So everything related to this talk is put in the data pipelines. And there are 3 examples here. Let me make it bigger. The first 2 are basically the data loader exercise. So the first one is this is loading the ImageNet data set. And for the purpose, this is using the TensorFlow. The first example is using the TensorFlow TF data loader. And you can try, so you can see this is basically a lot of pipeline defined here, shuffle, map, right? And then batching, etc., prefetching, everything is defined here. And then it's basically, the measurement is just low load the image batch by batch and measure how much time it take, and then measure the total throughput image per second. And in the submission script, you can see we try different kind of data loader. This was initially developed by Taylor. So you can try different number of worker and measure the performance. And you get a sense that increasing the number of worker will increase initially, but then later on saturate. And second example is the PyTorch data loader. In the PyTorch data loader also, you can increase the number of worker. And I think I have the data that I got last night. Number of worker equal to 1 is you get like about 600 image per second. And for some reason, this two data loader get lower, and probably because of the instability. If we rerun again, maybe it get higher. But if you increase to 4 worker, then immediately it's about like 1600 image per second, right? And then 8, you go to like 2016, still 2000, not increasing anymore, right? The third example is the ImageNet, the full training example. So you have the loading the data and then do the actual training. Just kind of quickly show this. This is the data set, right? So we define this how many samples in the whole data set by this length function, and load the image. This is the loading that, and then using open that file, eventually do the transformation and return the image, right, in a label. And this is the data loader, custom data loader, actually in this case. So you can try, and then the submission script also try to increase the different number of workers, and then measure the how many samples per second, the training throughput. So this are the third example. This ImageNet example is the overall training throughput, whereas the previous two examples are only the data loading throughput. So we don't have the compute inside here, but on the third example, we have the compute. Okay, so I think you can try this now.